The heat capacity of a particular object, which might be made from a variety of materials, can be defined as the amount of heat required to raise the temperature a specified amount. In this case, there's a direct relationship between the heat that is added to the object and the temperature change that occurs, and the proportionality constant that is given the symbol of C is the uh, gives the relationship between the heat and the temperature change. And so we can define this proportionality constant as the a conversion factor essentially between the heat and the temperature change. So we end up with an equation that states that Q, the heat, is equal to this constant heat capacity times the temperature change, which the temperature change is always the final minus the initial temperature. For objects that are made of pure substances, there are two different forms of the heat capacity equation, and the first form is in terms of moles, and we call it the molar heat capacity. And in this case, the equation would be Q is equal to the N, which is the number of moles, times the constant, which is the heat capacity with units of joules per mole degree Kelvin, and multiply that by the temperature change. And so this would be unique to the substance that is being studied. And the other form of this equation is for the so-called specific heat capacity, where the constant is in terms of the joules per gram degree Kelvin. And in this case, the equation looks very similar, except the mass is substituted for the number of moles. And of course, this changes the constant. But essentially very similar equations. As an example of how to use the specific heat capacity, we have a question that states we have 1 gram of a brass pin and it has a heat capacity of 0.630 joules per gram degree Celsius, and asks how much heat is required to cause the pin to change temperature from room temperature 23 degrees Celsius to 305 degrees Celsius. So we can take our equation, which is Q is equal to mc delta T, and plug in our variables. We plug in the 1 gram, the heat capacity of 0.630 joules per gram degree Celsius, and then multiply by our temperature change, which is the 305, the final temperature minus the initial temperature of 23. If we do our math, we end up with a value of 178 joules for heating the pin, and this would have 3 significant digits. If we were to look at a similar question, but instead of having a brass pin, we had a 1 gram iron nail, it has a heat capacity, or iron has a heat capacity of 0.449 because the material is different, the heat specific heat changes. And it asks again how much heat is required to heat the nail from room temperature to 305 degrees Celsius. Likewise, we'd plug these values into the equation. You'll notice the mass and the temperature change are the same, but since the specific heat capacity is lower, it's not going to take as much heat to cause this temperature change to occur. And so in this case, we end up with requiring 127 joules. So the crucial thing here is the heat capacity is the amount of heat necessary to cause a temperature change, and that specific heat is dependent upon what the object is made of. If it's a pure substance, then this object can be thought of in terms of the specific heat capacity. Shown here are some heat capacities, both in terms of the molar heat capacity values and the specific heat capacities. And you'll notice that in the case of the three different metals, they tend to have pretty low heat capacities. It doesn't take a lot of heat to cause a temperature change for a metal. And this is because all of the atoms are in very close contact with one another. On the other hand, if we compare that to other substances that we might be familiar with, for example, ethanol or water, they require quite a lot more energy to change the temperature. This has to do with how the molecules interact with one another. So, and water has quite a high specific heat capacity. As a final example, we have a question where we need to determine the specific heat of copper, given that 34.5 grams of a bar of copper requires 5.31 kilojoules of heat to increase the temperature of the bar from 24 degrees Celsius to 425 degrees Celsius. Again, the equation is Q equals mc delta T. If we rearrange this and get the constant, the heat capacity, all by itself on one side of the equation, we would have heat divided by the mass, which is also then multiplied by the delta T. We can plug in the values from the givens in the question. We have the 5.31 kilojoules as the value of Q. We convert that into joules because that would be the normal unit for heat capacity. And so we're going to multiply by 1,000, and the kilojoules will cancel. And the mass, which is the 34.5 grams, and the temperature change, which is 425 minus 24. We can plug all those values into your calculator, and so noticing that we're always going to have final minus initial for the temperature, so that we're going to end up in this case with a positive value for the heat capacity. And we end up with a value of 0.3838, and with only 3 significant digits, it turns out to be 0.384 with units of joules per gram degree Celsius.